It's a really simple relationship, and I'm just going to say that y is equal to 3 to the x. I think that's going to show up. That is looking really weird. So I've got y is equal to 3 to the x. And if I were just to make a quick table of values, of x and y values, I'm going to go as far as I can go in my head. So 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, 3 to 3 is 27, and 3 to the 4th is 81. If I were to plot these, and I had like this much space to put those points in. So 1, 2, 3, 4, sure. If I had to put this here, in order to have a big enough scale, I probably have to go like 20, 40, 60, 80. If I were trying to have a nice scale on this side, let's see, there's a comment that y'all can't see what I'm writing, and I don't know whether that is my pen or something's wrong with my screen sharing. So I don't know if someone on Zoom can unmute or type something in the chat. Someone else said they can see it, so I'm going to just keep going. So if I were to plot these points, and I know I'm doing this by hand, so it's not going to be perfect, but man, okay, so 0, 1, if that's 20, 1 is like barely showing anything at all. And even 3 is barely showing anything at all. 2 is 9, so that's almost halfway up. 3 is 27, so that's 20, 30 is about there. And 4 is 81, so that's all the way up here. And it looks like this nice, lovely exponential curve thing that we're all used to seeing. When we talk about a log linear or a log-log scale, specifically when I say a log linear scale, that implies that the y values have been logged and the x values have not been changed. If we were actually plotting this, what that does to the labels on my graph, it doesn't change the labels on the x-axis, but on the y-axis, rather than sort of that first tick mark being a 1, it's going to be something raised to the 1 power. So in this case, because I used a base of 3, I'm going to use my labels with a base of 3. So I'm going to call this 3 to the 1, 3 to the 2, 3 to the 3, and 3 to the 4. And if I did that, and I put those same points on the graph, they form a perfectly straight line. So we haven't done anything to the function. We kept the function the same. We just changed how we were labeling the axes. Now, if you're using Excel or Google Sheets, it's really easy to turn on the button to do a log scale on the axis, and it'll automatically change that for you. Now, this isn't the fun part of these problems. The fun part of these problems is coming up with an equation if we've been given some points. So I'm going to walk through that process, and I know that this is a super clean function, and I'm going to stick to a pretty clean function, but I'm going to give us a slightly different function, and we're going to have to come up with and like work back around to what the equation is. I'm actually going to open Google Sheets so that I can cheat and make my life easy. So I'm going to give us a function, And we're going to use the data to find a functional relationship between X and Y. So give me just a second here. I don't know how creative I want to get this morning. I'm not feeling super creative. So I'm going to give us some data here. We're going to have X values and Y values. My X values 1, 2, 3, 4. And my Y values 10, 50, 250, 1,250. So the first thing that I mentioned was the reason that we do transformations is because it's easy to find the equation of a line. So the first thing that I want to know is, are these data linear? Well, what it means to be linear is that as I move between the points, I'm always keeping the same slope. So if I wanted to check that by hand, one option is to plot these points and see if they fall in a line. But aside from plotting, my other option is just to see if they have a consistent slope. So if I think about that, I'm going to find the slope. And I'm just going to write this as like the slope between 1 and 2, between my two X values. And that slope would look like 50 minus 10 over 2 minus 1. That's a slope of 40. If I take a different pair and I look at the slope between points 2 and 3, then change in Y, so 250 minus 50 over 3 minus 2. Well, that's a slope of 200. These are not the same, so I know it's not linear. And one of our tricks to see if these data might become linear under a transformation is to try taking the log of the values. Now, the first thing I'm going to try is taking the log of the Y values to see if those work out to be linear. Technically, we can choose whatever base we want in terms of that log. I don't know about you, but my calculator only has a natural log or an ln button and an log, which is a base 10 in terms of the calculator. Does anyone have a preference, base E or base 10? Doesn't matter. Okay. So 1, 2, 3, 4, and I'm going to use base 10. So this is going to be the log of the Y values. And by the magic of the Excel sheet I have open on my screen, this is 1.6989. This is 2.3979, and I'm probably keeping way more decimals than I need here. 0.969. Well, if I do that same sort of check to see, hey, are my slopes consistent between points now? I can think about that slope between points 1 and 2 looking like my change in Y. So 1.6989 over, minus 1 over 2 minus 1. And it looks like that's going to give me about 0.6989. And if I check my slope on the next pair, 2.3979 minus 1.6989 all over 3 minus 2. And again, magic of the calculator. I get 0.69897. I'm calling those close enough. It looks like I have found the same slope between those points. So now that I have the same slope, now I can start building my equation. So I have the same slope when I took the log of the y values. Well, in general, if I'm trying to find the equation of a line, I'm thinking about y minus y1 equals m times x minus x1. But because this showed a linear relationship when I took the log of the y values, I'm going to replace for the y and the y1, I'm going to replace those with log of the thing, right? So my y, I'm actually going to write as log of y. And then I'm going to start plugging things in. So I can choose any point that I want. I'm going to choose the point 1, 1 because it looks the friendliest. That's okay. I would always recommend choosing the friendliest looking point. So I'm going to choose 1, 1. So I'm going to plug in 1 for my y1. I've got this slope over here. And I don't really want to drag around all those digits. Are you okay if I just call that 0.7? When you're working on your web work homework, you probably want to drag around more digits just to make sure that you're getting the right final answer. But I'm just going to call that 0.7 for right now. And then I'll have x minus 1. Well, the instructions to find the functional relationship mean that I need to do whatever kind of algebra pre-calc stuff I have to make that say y equals. Question.
Maybe a dumb question.
Probably not.
The original equation, the y minus y1.
So yeah, so this is just generally the equation of a line. So we kind of have two standard forms for the equation of the line. There's that one, and then y equals mx plus b.
Oh.
It turns out that in calculus, this version kind of becomes our go-to because this one relies on having a slope and some point, whereas this one relies on having a slope and specifically a y-intercept. So this one's just a little bit more generic. So we end up using it more often in calc. Yeah. But you can definitely work through the whole thing with this. We would just then have to like do the algebra to figure out what the intercept is.
Okay, and so we only logged one side, that's why we put log y.
Yep.
Okay.
If we had logged both sides, then we would also have logs on the x's. And we can do one like that next. Yeah.
Okay.
So on this one, I'm only going to have the log on the y. If I'm trying to get the y by itself, I first have to get the log y by itself. So I'm going to rewrite this to say log y is equal to, and here's where we have a choice. We can either distribute things out or not. I'm going to go ahead and distribute things out just because I think it makes the numbers clean up a little bit nicer, but it doesn't really matter. You'll just be pulling more parentheses around with you. So if I distribute this out, I would have 0.7x minus 0.7, and then I'm adding the plus 1 over here. I'm going to combine the 0.7 and the 1, run out of paper, which is really unfortunate because I'm going to have to flip my page over. And as soon as I do, I'm going to make a mistake. So everyone else needs to make sure this is written down so that when I flip the page, you're going to check me if I make a mistake. Yep. I did math in my head. So negative 0.7 plus 1, I think, is 0.3. We ready for the page flip? 0.7x plus 0.3. It's not too bad. 0.7x plus 0.3. 0.7x plus 0.3. Okay. I need to get that y by itself. Since I used a log, like an log log, it means that the base is 10. So to get the y by itself, I'm going to end up with y is equal to 10 raised to all the stuff. Now, I did similar problems to this with a bunch of people in office hours, like Friday through yesterday. Yeah, and so I want to pause just for a second because there are a couple of super common mistakes that I've been seeing people make. And this is the number one thing that is going wrong for folks. If I had 5 to the 2 plus 4, I know that's 5 to the 6th. But more helpful in this context, 5 to the 2 plus 4 is 5 squared times 5 to the 4th. The number one mistake that I was seeing people make yesterday comes from simplifying this thing. This is 10 to the 0.7x times 10 to the 0.3. Let's assume that the computer did the work for us, and we've got a slope, and we've got a point. So we know it's linear on a log-log. And let's say that the slope came out to be 2.5. And we know that one of the points on the log-log graph is, I am just making stuff up. Someone pick a number.
3.
So let's say it's on a log-log graph. So I'm going to make this the point. I'm going to make it actually, so natural log of 3, natural log of 7. By the way, that means that the base is E. And that's another thing to look out for, at least on the web work homework. Some of the problems specify that it's a base 10. Some of the problems specify that it's a base E. In terms of if you're just graphing something and trying to decide if it's log linear or not, it doesn't matter which one you go with. So now my base sort of equation of a line formula that was y minus y1 equals m times x minus x1. Now that I know it's a base E and I've got my points as ln's of stuff, this is going to look like ln of y minus ln of 7 is equal to that slope times ln of x minus ln of 3. But I still want to get the y by itself to find the functional relationship. Again, I have the choice whether I want to distribute this thing out or not. I think I'm going to go ahead and distribute it out. So I would have ln of y is equal to 2.5 natural log of x minus 2.5 natural log of 3, and then plus natural log of 7. You all can decide. Do you want me to turn this into a number on my calculator? Or drag all the stuff around? Well, I can either keep rewriting all of this stuff or turn that whole thing into just a number in my calculator. I'm going to leave it like this because then we get to practice more of our log and exponential rules. How about that? Okay, so to undo that natural log, I'm going to have e raised to all the stuff. It's not e individually raised to each thing. It's e raised to all that stuff. So this is going to look like y equals e to the 2.5 ln of x minus 2.5 ln of 3 plus ln of 7. And then I'm just going to remind us of that exponent rule, that if I have addition or subtraction happening up there in the exponent, I'm really going to switch that around to look like multiplication between things with the same base of e. So this is going to become e to the 2.5 ln of x times e to the negative 2.5 natural log of 3 times e to the ln of 7. Now it's time to pull out our log rules. It's tempting to make that e and that ln cancel out, but they don't. They will in a second, but they don't right now. I guess I'll just sneak it up here. One of our log rules says that if I've got something like 2 times natural log of 5, that's the same as natural log of 5 cubed. Because if I've got a number out in front of the ln, I can pop it inside. Or if it's out, or if it's inside, I can pop it out front. So in order to get this e and this ln to cancel out, I first have to take that 2.5 and pop it inside as an exponent. Same thing with this one. If I want that e and that ln to cancel out, I've got to take that negative 2.5 and pop it inside as an exponent. This one's ready to go. That e and ln are just going to cancel right out for me. So if I clean this up, if I get another step farther here, this is e to the ln of x raised to the 2.5 power times e to the ln of 3 raised to the negative 2.5 times 7.
The reason I did that is because, like when you raise it to the, when it's base e, it's raised by all of it, so then you can split it up. And
Yes. So when it's e, when I've got ln of y and I'm undoing that, it's e to the entire thing. And then we have to break it up as multiplication between the parts because we're really using exponent rules there. So now I've got x raised to the 2.5 times 3 to the negative 2.5 times 7. And if I was having to put this into WebWork, I probably would like do that part on a calculator, but you could also just type it in. WebWork is a calculator. So if you have a log linear, which is also called a semilog, and the graph is a straight line, then it came from an exponential function. Which super generically is going to be something like a constant times a base raised to the x. It's exponential because the x is in the exponent. If I had a log-log graph and the graph looks like a straight line, then this is a power function. Which means super generically, I've got some kind of constant times x raised to a number. And I don't know whether that was exactly the question that was being asked. But I hope it was. And really the reason here, I mean, does anyone want to? Okay, I answered the question, so I think I'm going to go with that. But if anyone would like to see me go from these equations to what the equation of the line is, I'm happy to do that. Does anyone want to play with generic equations? Okay, I got a taker. I'll be super quick about it. So if I start with an exponential function, exponential, I think I can spell. If I start with an exponential function, so something like y equals c times b raised to the x, and I take the natural log of both sides, and I'm just going to stick with natural log. It works with any base. You can do this as base 10. Natural log is a little easier for me to write, so I'm going to go with natural log. If I take the natural log of both sides, and then I apply log rules to the right-hand side, if I have multiplication inside of a log, I can break that apart as addition between logs. And then I can use that rule about I can use that rule about exponents inside of logs to bring this x down in front. So that I'm looking at ln of y is equal to ln of some constant plus x times ln of b. So my x has been freed from the log. My x is not inside of a log. That's why it is our linear term. My y is now trapped inside of the log, and that's why it is our logged term. If instead I start with a power function, and I called this y equals, I want to use like totally different letters. So I don't know. M times x raised to the k. Sure. And I take the natural log of both, and I take the natural log of, I can't even talk. I take the natural log of both sides. I'm going to end up with ln of y is equal to ln of m times x raised to the k. Again, I'm going to use that same log rule to break that apart and call that ln of m plus ln of x raised to the k. And then I'm going to, because I've got an exponent, I'm going to bring that down in front of the natural log. And I've got ln of y is equal to ln of m plus k times ln of x. So this time, my x is still trapped inside of the log, and my y is also trapped inside of the log. First, into a Google Sheet, I did a scatter plot by insert chart and then choose a scatter plot. Here is my lovely scatter plot. And what you can do is when you click on customize to customize the chart, you can play around with the vertical axis, turning on and off that log scale. So with my log scale off, it looks exponential. With my log scale on, it turned into a straight line. So I know it's going to be linear on a log linear plot. I can do that also just by looking at the numbers. So I've got my x values, my y values. So I made myself a new column taking the log of the y values. And what I was doing on Friday in office hours with some folks is just letting this calculate the slopes for me. So there are lots of ways to do this. I'm going old school. I'm essentially just letting this do what I did by hand. So I'm going to take my change in y values and divide that by the change in x values. And notice I'm doing this with my log y's and my regular x's. And if I fill down on that, my slopes are the same. So again, this is another way to know this was linear when I just use the log of the y values.